Well, good evening again to those who weren't here for the annual general meeting, and welcome to our lecture this evening, and jointly with the Geological Society of London. So, lovely, thank you very much indeed. Apologies for absence. Have you received anything for the... Yes, Rich and Stuart. Yeah, and of course, Stuart, John McCabe, and Ian Cameron McIntosh again. Would you have the meeting notes for the last minutes? Getting tongue-tied.
So the last meeting was by John Cook on Hetton Colliery and its railway. We had a rather good attendance, and it's been getting quite a lot of interest online as well, which is nice, and a number of questions were asked as well. Vote of thanks, Stuart Porthouse. Closing remarks, the President is present. Can we take that as true record of the meeting? Excellent. So, moving on, just a few notices coming up as we get the last few people in. Here are the dates for the rest of the lecture programme. We're very nearly finalised all of the other talks, just polishing off those around about Easter. But I can say that our next lecture is online only. That's joined with the Central Mining Institute in Poland, or Główny Instytut Górnictwa w Katowice, and we've got two Polish geologists speaking about how they're using the coal mines in Poland, predominantly in the southern part of Silesia, in a range of new and innovative ways. So as they close, what can you do with them? And it's not just mine, water, heat. Our early career group has got a rescheduled lecture, and again, this is online only, as James is splitting between Britain and Canada. That's on the construction of the the shaft at the Woodsmith mine in North Yorkshire. So do come along, we've still got spaces online for that. Our next in-person lecture is joint with the Institute of Corrosion, forward to having a whole host of corrosion scientists in the building as well. The other thing to mention is, of course, this is also having an Institute social night as well afterwards, very kindly courtesy of the Institute of Corrosion as well. So there's all the more reason for you to come along and join that as well. And then our next Institute lecture is actually on the new steam train, which has been designed using modern CAD techniques rather than just being a replica. So it's not a replica, it is an entirely newly engineered steam train, so hence is more efficient. Don't forget, there's multiple ways you can find out more about us online, whether that's predominantly via our fantastic and ever-increasing back catalogue of lectures on YouTube or via the social channels. And, of course, the best way to find out more about our events is via mininginstitute.org.uk/membership, where you can find access to a range of fantastic events and activities. You're at one of our superb lectures, and it's fantastic to see such an excellent attendance. We've got our annual dinner, which was just passed, and it was very successfully held upstairs. We've got a range of socials, so if you like going to the pub, we do that once every 2 months now these days. It's very good. And of course, we've got field trips. This one being a fantastic photo of when a load of us actually went off to see where the millipede lived. And that was a fantastic thing. Thank you very much, Neil. So don't forget, support us via membership. If you're interested, I have a stack of membership forms, and I do hope all of you will fill one out on the way out. Range of excellent membership benefits and opportunities on offer. And that's that, Steve, and so I shall hand back for you to introduce our speaker.
Thank you very much again, Andrew. There is nothing left for me to do now but to introduce our speaker for this evening. This lecture, is in joint with the Geological Society of London, and will cover the geology of the fossil forests, I hope, and exceptional sediment records and giant millipedes of the Northumberland Basin. The fossil of the giant Arthropleura millipede from Northumberland did make national headlines earlier this year, and I'm sure this lecture will provide an opportunity to actually meet and hopefully speak later with the leader of the team who actually found that. Neil Davies is a lecturer in the Department of Earth Sciences at the University of Cambridge since 2013. Having previously held positions at Ghent University in Belgium and Dalhousie in Canada. His research focuses on sedimentary geology, using the patterns and characteristics preserved in ancient sedimentary rocks to piece together clues as to how the Earth's surface and life operated at different intervals from deep time. I'm sure you'll welcome this lecture, especially those who attended the field trip in April. And for those who didn't, this is going to be a revelation for you. So I'm not going to mess around any longer. Can I please hand you over to Mr. Davies? Thank you very much indeed.
Thanks. Thank you. Yeah, thanks for coming. I mean, the title of the talk here is Carboniferous Park. I mean, it's obviously a nod to Jurassic Park, the Carboniferous being a different time period. The contention is basically that the Northumberland coast all the way up to, well, particularly the Northumberland coast, has got a particularly good kind of Carboniferous record. And if you know where to look and what to look for, there's a lot of little kind of snapshots and kind of time machines into that kind of past world. When we think about the Carboniferous, if you type it into Google and do an image search, first thing that comes up are lots of kind of reconstructions and museum dioramas of the coal forests. And obviously that's the most famous kind of aspect of this time interval. It's a time interval that's kind of characterized by these big equatorial forests, but also paleontologically significant that it's the first time that many amphibians are crawling onto land. So we have this kind of very well-known kind of ancient ecosystem. In Northumberland, I mean, pretty much the entirety of Northumberland is Carboniferous rock. There's not very much other than Carboniferous rock, but it's pretty diverse. You have a whole host of different things from the, sorry, did you say it was a little pointer?
Oh, sorry.
No, I can try and reach. Yeah, I mean, there's basically, yeah, you've got a whole host of different rocks. So obviously the coal measures are quite significant and famous, but there are other types of rock in the vicinity too. So there's things like all the moors and the Pennines, North Pennines, are made up largely of the kind of fell sandstones. And then there's things like the Whin Sill, this big igneous intrusion that cuts along Hadrian's Wall and out towards Lindisfarne. And I'm not going to talk about any of those today. I'm going to talk about some lesser known bits of the Carboniferous, and particularly about this site of this giant millipede. So to put a little bit of context, because this is really necessary to try and understand some of the things I'll talk about, the Carboniferous period extends from about 359 to 299 million years ago. And what's going on globally has a big effect on the signatures around here. So firstly, the main thing that's happening in this lower image here, you can see the star is broadly where we are. And what's happening tectonically is there's two large continents that are kind of colliding at this point around the equator. In the north, you've got Laurentia, which is much of Europe and America. And in the south, you've got all the southern continents, such as Africa and South America and Antarctica. And they form this supercontinent called Gondwana. Gondwana and Laurentia are colliding at this point. And here, we're right in the point of, in that kind of collision zone. So as these two big continents collide together, lots of other smaller continents are getting squeezed up in between. And the first thing that really happens in the Carboniferous is the formation in this area of a large kind of Himalaya-style mountain range called the Variscan orogeny. Now that Variscan orogeny is more prominent in Europe. In Britain and Ireland, it really skirts down the bottom. I mean, the fact that there were former large mountains here is the reason that southwest England sticks out as a peninsula. That Variscan mountain chain, mountain belt comes up through Kent, South Wales and into Southern Ireland there. But further north, there's still a lot of tectonic activity going on. And the whole of northern England is split into a number of small basins, kind of hollows in the lithosphere where sediment can accumulate. And those little rift basins are separated by kind of highland areas and sediments accumulating across this area. Obviously in those hollows, we get more sediment and more of a sedimentary record and more rock. But another significant feature of the Carboniferous is because we've got such large equatorial rainforests, they do a big job in global cooling, right? They're bringing down, carbon dioxide and creating really high atmospheric levels of oxygen, which is causing global cooling, which is causing big kind of ice sheets to kind of wax and wane on the Gondwanan continent. So if you go to, well, you've got coal in this region. If you go down to Australia at the same time, you've got kind of glacial deposits. And that kind of fluctuation of these ice sheets means that sea levels rising and falling, and it means that these basins are occasionally being filled in with water and occasionally they're being emergent. So that's the real backdrop to what we need to understand. Locally, this is the kind of geological setup. North of Hartlepool, basically, we're in the Northumberland Basin. And the Northumberland Basin is this large hollow interrupted in the middle by the Cheviot block. Okay, so the Cheviot Hill, as it now is made of older granite, and that's more buoyant on the kind of mantle, so that sticks up. But generally, there's a kind of low area here during the Carboniferous. The cross section at the bottom there just shows you this kind of the greys and the pinks are the rocks that were already there, and then the stuff on top is the stuff that got deposited during the Carboniferous. So you can see there's different thicknesses in there at different times. The general story is that the early Carboniferous, we see more marine deposits, largely limestones, and then the late Carboniferous, we see more non-marine deposits. And because sediment in this region was coming from the north, if you go north at the coast from Newcastle, generally you're getting into older and older rocks. So that's the kind of backdrop. And just to finish off with this kind of backdrop, if we look at the Carboniferous and its different sub-periods in a bit more forensic detail, these are the different types of environments and rocks we see at different times. These reconstructions on the left are just showing you two different time slices from within the Carboniferous, just showing you that, yeah, because the sea level is rising and falling, and because it's tectonic, there's substance and kind of uplift and tectonic activity, there's a lot of shifting back and forth during this 60 million year period. Now, the time interval we're going to look at are three kind of case studies, the last one being the millipede, that occur in the middle of the Carboniferous in what's known as the Serpicovian period. The three locations, basically, each you can kind of see as a kind of visit in a time machine to a different interval of the Carboniferous past. And each of these locations in the rocks there, if you look at them, there are details that give you really kind of these high resolution kind of postcards from kind of deep time. So the first one we'll look at is from Lindisfarne, from the north of the island of Lindisfarne, and it's in a rock unit known as the Alston Formation. So this rock unit at this particular location is about 330 million years old. If you look at the rocks in that area, you see a whole host of different features that tell you the environment at the time is both kind of deltaic sandstones coming from big kind of river deltas and these marine limestones, and telling this story of this fluctuating sea level due to the kind of glaciations at the time. Features that you can see in the rock are in some of the sandstones, there are these kind of diagonal cross-cutting lines that represent, as this block diagram shows you, the kind of internal architecture of some fossilized kind of river dunes. You see fossiliferous limestones pretty frequently. And in this region, what you tend to see is that these things are interbedded with one another. So you'll get one package of river sediments and then one package of marine limestones, and then it will alternate with some thin coals in between there. And that's just showing you these kind of cycles of rising and falling sea level in the region. Within this suite of sediments, there's a whole host of evidence for life in form of particularly trace fossils, these weird little kind of etchings and markings on sediments that through modern analogue we can tell were made by different kind of animals living at the time. So at the top there you've got a series of these little, this is the bottom of a sandstone bed with all these kind of almond shaped hollows. These are little resting traces where bivalves once sat. That squiggly line at the top with a kind of ridge through the middle is a gastropod moving through the sediment with some kind of feeding apparatus sticking at the top, building up these kind of levees as it went underneath the sediment. And then there's a whole host of other different patterns inside there, again from things like arthropods and worms. And as well as these animal traces, we also see a whole host of plant material inside there too. So it's not uncommon to find things like bark, twigs, and the roots of these different kind of Carboniferous plants. So the location at Lindisfarne hasn't been reported yet, but it's basically good evidence for one of these kind of ancient forests on this kind of delta top. The reason we can recognise this is that obviously throughout the coal measures and in older sediment, we see these features called stigmarian roots. These are the roots of these giant kind of lycopsid tree ferns that existed at the time. The yellow arrow is pointing to the main trunk of that root system. And you can see that it's covered in a whole series of holes. Those holes represent positions where little rootlets shot out from that actual plant, like on that reconstruction on the far side there. And those rootlets are arrowed with the little blue arrow there at the bottom. You can see that if you get your eye in, you'll see there's a whole host of these kind of springing off the side, like a kind of children's drawing of a kind of Christmas tree. And once we recognise some good examples of this, we can recognise some poor examples too. So the top left there is again showing you in green that kind of central bit of the root system, and then in yellow we're seeing these kind of little oxidized iron coloured rootlets that shoot off from the main kind of channel, from the main root. And then in the bottom here we've got another example of a really particularly poor example, but we're seeing those little root hairs. So even when we're not seeing those particularly good bits, once you start seeing these little flecks and lines of red lines inside there, you start to recognise these are rootlets. The reason this is significant is that at this location on the north of Lindisfarne, there's one particular bedding surface that runs across there that's covered in these little hummocks, picked out nicely in this photo by the kind of puddles that have been left behind inside there. And that whole surface is patterned with bits of these kind of roots, so in green, and lots of these kind of little etchings of these rootlets. If you walk along the surface, you'll find there's a whole network of these kind of root type features crisscrossing each other and creating this kind of mat-like network on the surface of the actual bed. Unusually in this location as well, we also come across a large number of kind of iron carbonate concretions inside the rock that are often quite circular. And many of these kind of concretions actually turn out to be the kind of the nodes where these roots are spreading out from. In other words, although these aren't really fossils, they're the kind of preserved remains of where there were fossils once. This iron carbonate is concreted around what used to be former tree stumps. So we see quite a lot of this kind of material inside there. Not something you traditionally kind of see as a fossil forest, not as good as some of the other kind of fossil trees you find around Northumberland, but significant nonetheless. And one of the reasons they're significant is if you look at kind of reconstructions of kind of Carboniferous forests, this is a very old one from 1844, it's generally kind of accurate in terms of the paleontological content inside there. But what it doesn't show is that when you have things like trees inside a sedimentary system, they themselves act to change the kind of hydrodynamics of the fluid flow around there. So in this example from Australia here, you see that the tree has created an obstacle which had allowed these kind of horseshoe kind of vortices to develop in its lee, and then you get this kind of scouring of the surface there. This location on Lindisfarne is full of shapes into the rock that we can kind of attribute to the movement of water and the deposition of sediment around obstacles inside there. So on the left here, there's an example of what looks like a tube inside the rock, which appears to be a situation where you've actually filled in a decayed kind of tree root. Up there, you've got an example where you can see there's an undulose kind of appearance with roots coming down from inside there. Effectively, this surface is a fossilized forest floor. With all those crisscrossing roots and the mounds of sediments around it, it's an accurate kind of representation of what was going on in that forest floor at the time. And you can map this out. I mean, this is a kind of detailed map with meter squares. All of those purple bits are kind of mounds of sediment around trees. So we get this good kind of view of a pre-coal or pre-kind of coal measures example of a kind of fossil forest. But what's unusual about this location is it doesn't just stop there. The surface is also covered with these kind of nested kind of rainbow patterns in the rock. These red patterns shown here with the kind of pink arrow, and they're in association with these little rootlets shown with the yellow arrow. And these things are all over the actual surface. The thing that's unusual about these is that these are another type of trace fossil, another type of animal activity, which belong to this this ichnogenus, as we call them, known as Zoophycos. And what that is a very complicated shape thing. This is a different example from Northumberland where you can see that the structure a little bit better. But the black line there, sorry, thank you. The black arrow is pointing to this kind of central tube, and around that central tube you have a kind of Christmas tree helter-skelter-like pattern of a series of kind of fans that radiate downwards. This kind of burrowing system is known in modern environments, but only from the deep marine realm. What it is basically there's an organism that's living in that central tube, and it's trying to get as much nutrition out of the surrounding sediment as possible. So it's staying in one location and expending its entire life and all its energy getting nutrients out of that sediment. In the present day, this is well suited to living in deep marine environments. But there was a relatively recent paper by some Chinese authors who recognized that actually, I mean, if this was deep marine, It'd be weird we're seeing deep marine fossils in the middle of a forest. But this Chinese paper recognised that actually, as you go further back in geological time, the range of these shapes wasn't just deep marine, it was actually near shore. These were some of the earlier animals that lived in near shore environments. The reason that they've retreated to kind of deeper marine environments is simply other things have evolved. Right? It's no use spending your entire life living in one place and feeding on the sediment there if something's going to come along and outcompete you or eat you. So these things migrated through time. So it's an unusual kind of snapshot of a particular type of feeding, unique to the kind of Carboniferous in nearshore environments. And the reason we see it on this forest floor is basically if we look at the rocks above the kind of forest bed, we pass into marine shales with trilobite fossils, and then into kind of limestones, into marine limestones. So what we're seeing there in Northumberland is this really detailed snapshot of effectively a drowned forest. At some point in the Carboniferous, when we've had an interval of kind of glacial melt, because these things are fluctuating back and forth, the whole thing has been flooded. And that surface has got about 30 different trees on the surface of it. And it's, again, this nice little snapshot of what's happening locally due to these global kind of effects of glaciers and these regional effects of the tectonics of the Variscan orogeny. So our next little time machine stop is a little bit further north, just south of Berwick, at Scremiston. And at this location, we don't see the forest floor, but we see what's going on just offshore in the shallow marine waters. Again, the signatures of the Alston Formation are similar. We've got things like, we've got some coal measures inside there from these delta top environments. We've got these kind of nice corals representing marine conditions. And we've even got on some of the sandstones these little patterns which appear to be kind of jellyfish strandings. Okay? So there's a really high resolution kind of record inside there. But one location in particular of particular interest, and that's this cliff face here. This cliff face has only been exposed for the last 5 or 6 years because on the top of the cliff here there's a road that collapsed into the sea in the 1950s, and it's taken 60 odd years for all the kind of junk that was left behind, the debris, to be washed away. It was cleared away by a storm finally about 5 years ago. But the reason this is an interesting location is that if we look at the rock type there, we see lots of thin interbedded sandstones and mudstones. So the sandstones are kind of light coloured, and then these lines in between, these darker lines, are these kind of organic rich mud rocks. Not quite coal, I mean there's a thin coal measure on the top, but these are just kind of organic rich muds. But when we look in more detail there, we start seeing real patterns emerging inside this pile of sediment. It's not just interbedded sandstone and mudstone, but rather packages of sandstone and mudstone interbedded, numbered here, 1, 2, 3, 4, and they're interspersed with these layers that are just mud rock. So we're seeing this kind of like barcode type pattern inside the actual rock. And what's unusual is that there's a repeated number of sands within these packages. It's always between 14 and 20 packages of sand inside there. So if you're seeing that kind of rhythmicity inside the rock, there's got to be a kind of reason. You need to appeal to kind of natural rhythms to work out what might have caused that. In this particular instance, that kind of 14 to 20 laminae is pretty tidal. If you look at, I mean, this is the measurement here of the thickness of the different individual laminae inside there, and you'll see that as you come into one of these sandstone packages, that they're initially quite thin, and they get thicker and they get thinner. That pattern is exactly what we see in kind of spring and neap tidal cycles. In any tidal system, the flood tide tends to be a little bit stronger than the ebb tide, unless there's like local kind of causes that mean that's different. But any instance, one tide is stronger than the other. If you've got one stronger tide, then that can move sand particles, whereas a weaker tide might only be able to move mud. Each one of these individual layers here is actually a day of sedimentation. So even though it's 330 million years old, this package here is a couple of months of sedimentation that's been preserved. And the reason we're seeing this really high resolution record is, again, just an artifact of where we are at the time. We're here at the time that these were being deposited, at the end of this really long kind of seaway that extends between Siberia and kind of Greenland, all the way down through the kind of Baltic and like Denmark, Poland area, up to here. And you would expect that actually, because we're in this really kind of elongate sea, that you wouldn't really have many tides. In the Mediterranean, you don't have really big tides as you go further into the middle of the Mediterranean. But in this particular instance, because we were sandwiched between the Cheviot block and then the kind of highland areas of Scotland, you'd get resonance effects that kind of amplify these kind of tides. And further, because we're in a situation not too dissimilar from the Indus Delta in India at the present day, these kind of tropical kind of mixtures of kind of sandy sediment, kind of rainforest type conditions, and then this offshore sediment. If we're in one of these little pockets in between there, you've actually got this little tiny pocket where you can accrue quite a lot of sediment and fill it up quite rapidly. So within a record that's generally kind of incomplete, we actually see these really high resolution records. What's further unusual about this is that those packages of tidal rhythmites aren't the only pattern that we see there. Many of the surfaces are covered with these little dots, this kind of Dalmatian-like pattern. And those little dots have got their own kind of structure that repeats every time. Each one is a kind of a central piece of dark mud surrounded by a rim of sand, creating these kind of bullseye patterns. And you see it on sandstone beds and you see it on mud beds. What these are burrows. They're burrows of animals that have gone through that kind of mixture of sand and mud, excavated the sand at the top and left it around the actual rim of the burrow surface. And what's unusual about these burrows is that we've tested these statistically, they are all equidistant from one another. They don't cross over, they all remain the same kind of distance from each other. And that seems unusual, but there is actually a long-lived organism that can kind of explain that. And these unusual things called phoronids, which currently live, they're referred to as worms, they're not really worms, but they're unusual animals. They live in kind of tropical waters in a larval state. Their lifespan is a matter of hours, so less than a tidal cycle. And the larvae will settle down as the tide goes out, they'll colonize the whole surface, they'll live for one duration of a tidal cycle, and then the larvae extend off again into the water column. The reason they're all equidistant is that when they settle down, they can't compete with each other because they feed through these things called lophophore nets, and they all have to be equally spaced from one another in order, otherwise they'll be entangling with each other. So these things have these really repeated patterns. This is what their burrows look like, and that's what we're seeing in this location. And you can see this in cross-section when you look in there. You see all these little phoronid burrows with the surfaces like that, and then you've got the individual tubes coming down from inside there. So that's quite interesting, but what's unusual about that is that then we ask the question, why don't we see these every day? If every one of those layers is an individual day, and every one of these packages of kind of burrows is this phoronid community, why aren't we seeing these things on every single layer? Why aren't they all overprinting with one another and recycling the same sediment? And the answer there, I mean, it really comes down to something quite important that hasn't really been appreciated in Earth history before, and that's simply that if you look at modern kind of burrows, these are on the tidal flats at Lindisfarne, so these aren't phoronid burrows, they're just worm burrows, but they tend to occur in patches and clusters depending on where the tides have allowed things to colonize at different times. In other words, you don't colonize everywhere at the same time, you colonize individual patches. And the reason we see there in Scremiston just a few different layers with these things colonized is simply because the patch that happened to end up being the same patch that was exposed in that cliff face would have shifted elsewhere. The bits where they would have colonized in other days are now missing because they've been eroded, or they're hidden inside the actual cliff face. And this is quite significant. I mean, this recognition that the rock record has these really high resolution records is making a big change in the way we understand historical records of deep time. So these tidal deposits are quite a useful kind of indication of that, and it really hammers home this message that just because things happened a long time ago doesn't mean they took a long time to happen, right? And we get this high resolution snapshot of the Carboniferous seafloor here. There are other burrows in that section as well, incidentally, where we don't quite see the same thing, but rather a large tube that itself has been filled in with these kind of tidal rhythmites. That's a different kind of organism. Things like crustaceans, so lobsters and crabs, when they burrow, they live in a hollow for their life. They keep it empty the entire time. When they die, you actually have a void that gets filled in later on by these tidal sediments. So we can pick out different kind of animals that are living in that area too. Okay, so finally, the last little slot, the main bit of this, is this giant millipede. Okay, so you'll have heard of this giant millipede, I think. it made quite a lot of press, and this is only a snapshot that can fit on one slide. There's things here from Brazil, France, Sweden, Ukraine, Saudi Arabia, Poland. It was all over world media. We found it was on the BBC, obviously. This was a reasonably accurate kind of reconstruction in the Daily Mail, where the size of the organism was compared to Peter Crouch. And this is a less accurate representation from the Sun, where it was compared to a mini. And I mean, I think when we were being interviewed, I'd said that you'd struggle to get it in the boot of a Ford Fiesta, not that it was the same size as the Mini. It's about the same size as Peter Crouch, not the same size as the Mini. So what this thing is, right, it's this fossil called Arthropleura. And again, if you do a search for Arthropleura, it's a very common denizen of these reconstructions of these Carboniferous rainforests. People often show these giant millipedes and giant kind of dragonflies living in these environments. And it has quite it's got a mild kind of popular science reach. It appeared in Walking with Monsters, and then later on I discovered apparently it's in a children's horror story written in America, a book there about a giant Arthropleura living in somebody's basement. But despite the fact it's relatively well known, it really wasn't until a couple of years ago. There are only 2 large fossils of this preserved. So the 2 fossils that were known were both from Germany, and they were both from the late Carboniferous. There was this one here, which is in Frankfurt, and this small example there. We've not got a complete fossil of a large one of these giant millipedes. There are a few from France that are complete, but they appear to be juveniles. So they have the same kind of structure, but they seem to be very small. So in terms of complete fossils, this is the best that existed. There are plenty of other fragments, so individual pieces, that you could ascribe to being from the same organism by reference to this. But generally, the reason that people knew there were giant millipedes at the time is more due to their trace fossil record, that there are, throughout rocks of the Carboniferous age, so such as these on the Isle of Arran, there are these kind of tramline patterns of footprints of an animal that has to be of a considerable width and have multiple different legs in order to make these kind of trackways. But what we knew from these trackways was that there were large animals. But if you can, these are the photos of those 2 German specimens shown at the same size. Those things were clearly smaller animals than the things that are actually making the trackways. Okay, these things are obviously these things occurred at multiple different sizes, but neither of these are the same width as these Isle of Arran trackways. Now that trackway record's pretty good. Basically, animals tend to leave more footprints than they do skeletons, right? So you have a much better kind of record of these trackways. And not quite in the Northumberland Basin, but not far north in Fife, in similar age rocks, there's a whole host of these different trackways that are apparent. If you walk along the coast around Anstruther, you'll find blocks that have got loads of these little these kind of tramline trackways of these large kind of myriapods that were walking around at the time. But these were really the most common evidence until we made this discovery in early 2018. So just to explain how we made that discovery, it was entirely by accident. Basically, I and 2 PhD students had decided to go on a trip in January just to go and visit every geological period in Britain in the correct order, which basically meant a 3,000-mile round trip of Britain, staying in Travelodges in early January. So we'd already been through the Precambrian of Leicester, the Cambrian and to Silurian of Wales, through Herefordshire. And then we shot up towards Northumberland, because I had kind of family ties in the region, so we came up here, and then we finished off by going down to the south coast and from Devon across to Kent and up East Anglia. But when we got to the Carboniferous in Northumberland, that's where we found this unusual fossil. So the location we found it was here in Howick Bay. And at this location, we see both the Alston Formation we just talked about over there in the distance, and then the Whin Sill is a little bit further along at Cullenose Point, and then also this Stainmore Formation. This is the unit in which the fossil occurred. The reason we see them both is that at this location there's a feature called the Howick Fault, which will become important later on. It's basically a big fault that separates these 2 units, and it formed at the same time we were having the tectonic activity that was creating these basins. It's related to that kind of Variscan mountain belt that's down in kind of the southwest and South England at the time. We know how old this is because there's a conveniently dated unit called the Licker limestone that runs through there that's got quite a lot of fossils that really date it quite accurately to being in this Serpicovian interval. So that's the logistics of where we are. This block here is where we found this fossil millipede. It's basically a block that has fallen off from the cliff face there. Now, I'm not entirely sure when this fell off, but as I've been back every year, this is somewhere, it's sometime between 2016 and 2017 this block fell from the actual cliff face. And when we encountered this, if you imagine this photo was taken, this is the last photo I had before we found the actual fossil. This is about 4 o'clock on the 6th of January, so it's colder than it actually looks. And the first images I have aren't particularly good. They're quite dark because this is the block here, and this is Will, one of the PhD students. This is where we found the fossil lying inside. We did go back in the morning and had a look in a bit better light. And this is what the block looks like. It's basically, on its side, 2 layers of sandstone that have fallen from the top of the cliff and they've split in the middle. And fortuitously, that split is what revealed this large fossil inside there. It's 3-dimensional. So on this side of the slab here, you've got this kind of raised mound, and you can see there's these little lines coming off the side of it. And on this side is where much of the actual fossil itself occurs. You can see there are these kind of these ribbed kind of patterns and these feathery kind of lines off the side. I'll explain what those are in a minute. Basically, once we'd recognised what this was, it took a while. We had to track down who owned it. It turned out to be the Howick estate. They gave us permission to go up there. It was also next to a fulmar colony, so we had to wait until May before we were allowed to go and collect it. So we waited 5 months, got the permission, and went down there and managed to get this thing out so we could look at it in more detail. This is down on the shore. If you've been to this location, there's a small little lay-by on the side, and then there's a path that goes steeply down the cliff for about 20 metres or so. It took 4 of us to carry this out. We bought a duffel bag for the occasion, so we stuck it inside there and lugged it up the top. I'm not entirely, there were people picnicking on the top of the cliff when we were doing this, and I'm not sure what they thought we were doing, but we managed to get it back, got it into a hire car. The hire car survived the journey as we got back to Cambridge until we bottomed it out on a speed bump as we were getting back, because we'd got 120 kilograms of rock in the back of it now. And this is what we were able to do with this then. We were able to see this in better light and look at what's going on. So what we see here are the fossil in 2 different slabs. And these are kind of, if you imagine these kind of fit together and they've pulled apart like this. This is this rounded surface, which is a little bit more evocative when you see it, because you can see the shape of the organism. But this is much more informative, this one here. And this slab, these lines here are effectively the centre of the actual animal. So if you think about a modern millipede, or think about a woodlouse, they have a kind of central area where there's a number of different kind of skeletal parts to that animal. And that's this central part. And coming off the side here, these feathering off areas, this is one side of the animal. So this is one side of the bits that would have been kind of going down towards the ground. So we've only got 2/3 of the width of the animal preserved here, and we don't have the whole thing. It would have carried on quite a way down there. We didn't know at the time whether, I mean, these ribs get smaller as you go to one end. We didn't know if it was the front or the back of the animal, but it was through talking with experts who'd worked on these before, but this is probably, it's not the actual head, we haven't got the head, but it's just behind the head and going back a little bit. There's a few details on there, on that surface, that show more information and allow us to tell that this was this millipede. Firstly, there's this kind of rough texture along the side of many of these ribs. This is where there would have been this kind of membrane that would allow the animal to stick together in life. There are these kind of patterns, these lines and striations on the actual tergites, the original ornamentation of the animal's skeleton. And the other thing that's unusual about these is that when we got this out, both unfortunately and fortuitously, it's very indurated sandstone. So hammering this thing out, it basically split and broke down the middle. But we would never have broken it deliberately, but it enables us to see a cross-section of the actual thing there and see that actually the individual so the tergites are basically the name for these segments. The segments are actually filled with sand themselves, and that's quite unusual. What it suggests is that given that they're not just completely compressed into one pattern like the German specimens are, this thing must have been filled with sand before it became fossilized. In other words, it kind of suggests that this isn't the actual animal itself, but rather a molt of its actual skeleton. So it molted its skeleton, as most arthropods do, to grow, and then that debris got filled in with sediment in the environment, and then that got fossilized. Another thing that's interesting about the fossil is that it's kind of got another fossil hidden underneath it. The main bit that you can see there has got these patterns I was talking about, but there's a kind of ghost-like smear of this kind of carbonaceous material that's slightly offset from the main fossil. So in this example here, these circles are showing you particular shapes of these side tergites. And then these little ghosty patterns up here are the same things. It's like the animal has been, or the fossil has been smeared inside the rock. It's left an imprint of where it was, and then it's moved along the actual surface of the rock. And there's not really a paleontological explanation for why that would be. Turns out the answer's simply due to exactly where it occurred. I told you we were right next to this Howick fault. Well, the Howick fault has got a whole host of individual little slivers moving off it. And where the fossil came from, this black circle, and fell down the cliff, is right in the middle, right next to this kind of master fault. Basically, this animal and the fossil were so big that they actually got faulted. Right? These things remained inside the actual rock as a material discontinuity, and because these faults were sedimentary, so they were active at the time the deposition was ongoing, it basically smeared the sediment and squeezed the actual fossil inside there. So, I mean, this doesn't really happen very often, but it's simply a result of its size. So this is a PhD student for scale showing you where the actual, this is when we thought it was the tail end, which is why it's the wrong way around. But this is where the bit of the animal is. Now, in terms of how big the animal is, these small examples from France mean we know how many tergites one of these organisms should have. It should have about 28 to 32 individual tergites, and we've got 14. So we know we're only looking at the front bit of the animal. So we wanted to calculate and work out how big this thing was in life. So we know we've got 2/3 of the animal, and we know the fossil itself is 36 centimetres big, so it was easy enough to calculate the kind of width of the animal. It's about 55 centimetres. But we also know from these smaller examples that they all have a very defined kind of width to length, or length to width ratio. So we could then calculate this thing is actually originally would have been about 2.63 metres long. All the small examples have got this kind of 4.78 length width ratio, so we assume that's about the same. So once we guessed that this, or estimated that this thing is going to be about 2.6 metres long and 55 centimetres wide, we could try and work out how heavy it is. So people in the past have tried to estimate how heavy these things are by calculating them as cylinders, but clearly millipedes aren't cylinders entirely. They've got lots of little shapes inside them. So we tried to calculate it as a kind of hemi-cylinder, but that didn't really work either. So in the end, we got somebody to make a little 3D computer model so we could actually calculate the internal volume of this thing from the dimensions we got. Then and this is quite a hard thing to find out. It's quite hard to work out what the mass of a modern millipede is, but there are papers out there. So by looking at the mass of a modern millipede and working out the volume of this thing, we reckon this thing weighed about 50 kilograms. Okay, so it's a pretty hefty organism. So these are the superlatives that we've got. Firstly, we've got the largest Arthropleura fossil. Okay, compared to all the other ones worldwide, this is a much bigger actual fossil. It's the same size as some of the largest and widest known trackways of these things. So it really is the culprit responsible for making these trackways. But it also is much bigger than the largest previous reported arthropod organism in the world. Again, this is something we stole from the Germans. So the previous largest organism known was this Devonian sea scorpion from Germany. Ours is bigger, okay, as an animal, and it's also the largest arthropod fossil, just beating out, I mean, admittedly this is a complete fossil from Canada at the same scale as a person, but it's marginally larger, okay. So it's got all kinds of superlatives, the biggest fossil, the biggest kind of arthropod that ever lived. And these large arthropods are of interest, okay? People are interested in knowing where these things and how these things lived. So the context of the Howick site is pretty good because we can see a number of different clues about what's going on. Firstly, amidst the kind of sandstone that the fossil came from, we see, again, evidence of tidal deposition inside there. So we know we're kind of pretty near to the shoreline. We also find fossil plant seeds of a type of tree known as the corditalian, reconstructed there, which is kind of a dryland tree. Basically, in the Carboniferous, the flora that dominates the coal swamps are these lycopsids, but as you move towards the end of the Carboniferous and the coal measures disappear, that's one of the reasons they're being outcompeted by kind of dryland plants, and Chordates is seen as one of these kind of dryland plants. Also, in the same succession, there are these, and these have been reported before, these footprints and trackways that have been attributed to what's known as a tetrapod, this Anthracosaur tetrapod, these kind of large amphibians. And so there's a number of different things there. We can see the kind of organisms this thing was sharing its habitat with, and we know where it was living. And that enables us to make this relatively kind of accurate reconstruction about where it'd be living in this kind of open wooded habitat right next to the actual coast, okay? What you'll notice is that it isn't these kind of coal swamps. And actually looking back in some of the really old literature on these things, although these things are often reported as living in these kind of coal forests, the reason for that is that many of the original fossils and the partial fossils were found from coal mines, but they weren't found in the actual coal itself. They were found in the sandstones that occurred in between there. So in other words, these things weren't living in the actual rainforest. They were probably living on the periphery of these rainforests in these kind of sandy habitats. The reason they came out the kind of spoil of the coal mines has given this rise, this kind of lie they were actually living in these kind of coal forests. But actually these were probably much more near shore kind of things. And that makes sense because these things could then move aqueously as well. They wouldn't dry out and desiccate. The other thing that's interesting about this fossil, it spurred us to go and look at some of the other reports. This is a map reconstructed to the Carboniferous, showing you all of the large fossils, the small fossils, and the trackways known worldwide. And you'll see that worldwide, they're all known from this really restricted area in Europe and America, which when you reconstruct it, is pretty much along the actual equator. The interesting thing is if you look at, obviously the equator moved through the Carboniferous as the continents moved around. And when you put these things on maps with the red line here being the equator and the dots being the fossils of those ages, this is the Howick specimen here. Okay, so it's very early in the range of these fossils, and actually it's the first evidence of the body fossil evidence of these things being giant. It's just south of the equator. If you look as you move through the kind of later Carboniferous and into the Permian, the general track of where these things occur worldwide moves south. That's simply because the continents were moving north and these things were remaining at the equator. In other words, the youngest evidence for these arthropleurids in Britain occurs from the late Carboniferous. They've disappeared by the kind of Permian, but that's because by the Permian the equator is much further south in Spain, where these things have started to recur for the first time. The interesting thing about this is that when you put these things and look at kind of other records, like kind of global records of oxygenation, oxygen's been kind of suggested to be a big spur for why things could get so large. It doesn't match up. Their appearance and disappearance doesn't match with these oxygen curves. So there must be another reason there, an unknown reason. But these things live near the equator. They were the largest animals on land at the time. They might have been feeding off these different tetrapods. Certainly there's lots of nutritious seeds around. We don't know why they got so big, but we can rule out oxygen as an actual reason for that. So yeah, just to summarise that very last little time travel pit stop. You know, this is the largest arthropod fossil in the world. It's the largest ever arthropod, and we now know that these things predated these kind of oxygen spikes. So the reason they disappeared might not have been a change in atmospheric oxygen, but maybe they got outcompeted by kind of reptiles in the Permian. And we know that they lived in this kind of open wooded habitat, not in the Carboniferous rainforests. So yeah, that's the talk really. I mean, basically the main kind of take-home messages are that these different places along the coast are all postcards from kind of different intervals of deep time. You can trust them to be kind of true records of things happening on days and weeks and months. And you can go back and walk up the coast and you'll find evidence of these giant millipedes, drowned forests, and these thriving kind of seafloors. And the key message is there's more to be found, right? There's a lot more stuff out there, so more people looking, the better. Thanks.
Well, it's just amazing. There's so many things there that I wouldn't have even thought of. Well, of course, I'm not. Thank you. I'm not even a specialist in any way, but you know, for a normal person like myself, just a lay person, some of the things that you've discovered there are outstandingly amazing. I mean, I can't say anything more than that. But what I can say is, would anyone like to ask any questions? I'm sure.
Yep.
Anyone there has anything they'd like to say? I think they're all dumbfounded, to tell you the truth. Oh, here we are. Could you state your name and position, please?
I'm Carl Erickson.
Wait for the mic, please, so that most people can hear.
There we go. My name's Carl Erickson, and I just wondered, have you seen the trackways at Whitley Bay?
No. But I mean, I think there's got to be more out there.
There's a pair just on the way to St Mary's Island by the causeway, a pair of parallel overlapping tracks.
Yeah.
And having read your paper, we went and measured them.
Oh, yeah.
And 57 centimetres, the widest one, external.
Yeah.
Which puts it in the same ballpark.
Yeah. No, that's very interesting.
And that's younger.
It is younger, yeah. But that's in the range. That's the same age as the 5 stuff.
Yeah.
Okay. No, that would be interesting to go and.
I've got pictures and all sorts for you.
Yeah, that'd be great. Yeah. Well, I think there's more because someone from Beadnell contacted me after the paper came out and said they'd seen some after the storm had scoured, or after a storm had scoured down, but we went back to Beadnell. It's now covered by sand, but it does look like the same kind of thing in there. There's got to be a lot more of these kind of trackways knocking around.
Yeah.
You know, these things have left their trackways in Fife and their body in Northumberland. They've got to.
And just one other thing, I've got photos. Been to Howick. I run lots of geological trips.
Yeah.
Been to Howick numerous times over the years, and I've got photos that I think show that block on the ground.
Yeah.
2011.
2011. Okay. Yeah.
I've got one from '94 which shows the Clifford Tap.
Yeah.
And then 2011 it wasn't specifically taken to that. It was
Yeah. Well, that's the thing. I've only got photos to rely on. I wasn't looking for it. So
I've got the fault, and I go, well, you know. 5 degrees that way, and it would have the block in as well. I think it's been there for a bit longer than.
Yeah, because somebody told me they'd seen it in 2017, which is before we'd seen it. They didn't know what it was.
Yeah,
but,
I think it's been certainly there a little bit longer.
Yeah.
I'm Ian Kill. Curious about from the fragmentary nature of the specimens that have been found worldwide, to what extent you're able to reconstruct head parts in particular, and whether that has any bearing on whether you can count all of these specimens belonging to one species or maybe some sort of evolution of different species.
Yeah, I mean, there are no heads. That's the problem. There's one head in there's one head on one of these tiny French specimens, and that's the thing that's been used to reconstruct all the heads, but it is a big unknown. And the thing is, these things might be, again, they might be more molts than they are actual fossils themselves. That might be why we're seeing so many fragments of these things, even large fragments like this, but not the actual head itself. That hasn't been found. I did think for a while that the head might have been cut off by the fault, and it might have still been in the top of the cliff. But I think if it was there, then it would actually be a little bit, I mean, it would probably been eroded away already. So,
good luck with finding that one,
Yeah.
I asked another question.
Yeah.
You mentioned zoophycus quite a lot,
which
is obviously really quite common in a lot of the limestones, as well as the location you noted. Do you have any ideas on what sort of animal would have actually created that?
No, I mean, I think it's made by lots of different things. So I think like multiple different kind of worm-like organisms have made it in the past, because it exists from the Cambrian through to the present day. So there are Cambrian examples. And they've lived in different environments. So as with lots of trace fossils, it might just be a strategy for living in a particular habitat rather than being a
bit of evolution around different animals that are producing the same sort of thing.
Yeah.
Are there any modern analogues?
I believe there are, yeah. There's certainly Cenozoic examples. I mean, but obviously, if you were to look at these things, you need to get box cores from the deeper marine environments and look at these things in 3D, which is hard in loose sediment.
Right. one more?
Sure. Yeah.
Sorry, last one.
Yeah.
Given that there's no correlation between the oxygen levels and the size of the animals, how on earth do these things breathe?
Well, that's one of the things that maybe if they were close to water, they might have been going back into water repeatedly. They might not have been totally kind of subaerial organisms. Again, this is my knowledge of Arthropleura has largely come from finding that thing and learning quickly on the job. But we had a guy called Jörg Schneider in Germany who is the world expert on these things. He's not sure if they might have been air breathing or if they had gills. It's not clear. None of the surfaces have got these little spiracles that you'd expect from these kind of organisms to be breathing on land. So it is, again, it's this issue of incomplete kind of fossils. It's certainly a large animal, but it's not entirely. There's a lot of unknowns. It's not clear what they ate. It's not clear how they breathed. We've only been able to clear up a couple of bits and pieces on there.
Yeah, so we're waiting for a trace fossil with which has got something else in the trace as well as the leg movement, or a nice soft part preservation.
Yeah. I mean, I think, in terms of what they've eaten, there was one of the fragmentary fossils from Scotland had been found in association with lots of kind of degraded kind of seed debris, so it was thought they might have been herbivorous. But that's the level of understanding about some of these kind of features.
Great. Good, thank you.
Anyone else? No? No? Well, I'm sure that Professor...
Oh, sorry, was it?
Oh, we have. Oh, sorry. It's like an open.
Thank you, Brenda Turnbull. I just wanted to know what stage the research in the specimen is at and where it might be at the moment, and is there any chance of us seeing it back up here?
Yeah, well, I mean, this is currently in the Sedgwick Museum in Cambridge. It's due to come here next year, but that's down to museum people, and museum people talking to museum people. Next year could be, well, we might be waiting 300 million years.
Let's hope not.
Yeah.
So is it in a case on display in the Sedgwick?
Yeah.
And which museum do you know?
The Hancock or whatever it's called now. Yeah.
Thank you.
Yeah.
Hi, Leslie Dunlop here. Just wanted to make an observation. You said that the fossil you found was probably a moult.
Yeah.
And just going back to your early slide on the size of the fossil, could actually be the size of the mini when it's adult in its next stage.
Yeah.
You just, just hadn't quite got there.
Yeah.
Hold on. Anyone? No, that's okay. Right. Well, I think if we dried you up a little, but I'm sure Professor Davies will be available possibly a little later. I don't know how long you're staying with us. I know you have to get a train home, but I'm sure he would be willing to talk for a moment or two if you approach him very quickly. Yeah. Anyway, thank you very much indeed from myself.
Thank you.
You have actually amazed me with your detail. And could I ask David Granger to give a vote of thanks to you for your wonderful lecture?
Right, Mr. President. Yes. Mr. President, ladies and gentlemen, I think we've been given a fantastic lecture tonight by Professor Neil Davies. I was lucky enough to go on the field trip that he ran earlier in the year to visit the Millipede discovery site in Northumberland at Howick, which is a wonderful day. The weather was kind to us as well, which made a pleasant change. But that was very interesting, and to see the actual location, and I think so much about geology, and I'm a geologist, is serendipity. I mean, if they'd gone to that beach and turned the other way, instead of going to turn right, if they had turned left, they'd never have found it. And maybe it would have been eroded away, and we'd never have had the experience of this lecture. So that is something that is remarkable. How can I re-talk about the lecture? It was, I think, going back to being a geologist, there's an old adage that the present is the key to the past, right? And we always taught this, first year geology lectures. And I think this has shown that Professor Davies is using present to interpret what was happening in the past. These trace fossils, the way the trackways are produced. We can see this in rocks today being formed. So that's very, very, very interesting. And I love these burrows that maybe last a day, an animal living a day to produce these burrows. It's amazing that you can get down to this detail. I mean, yeah, being a geologist, I've never found anything quite like this, but trace fossils I've been very interested in, and Cruziana, beautiful trace fossils of trilobites crawling through the mud on the sea floor 400 million years ago, perfectly preserved. These are fantastic things to find. But, I mean, the millipede fossil is just mind-blowing. The largest one that we know of. And it's a molt. Maybe someday they'll find the actual fossil itself. What an achievement that would be. But in the meantime, so much has come out of this work that Professor Davies and his colleagues have done on the Northumberland coast. We're privileged to live in such a wonderful area for geology. Every time you go out on the beach or in the hills, you can see the results of geology. And as I always say, in the end, everything comes down to geology. That's being biased, but everything comes down to geology. So thank you very much indeed for a fantastic lecture. And maybe when you find another famous discovery, you come up here and talk to us about it. So thank you very much indeed. Can you please show your appreciation? Thank you.